Well, welcome to our talk. I'm glad you could make it. I'm Jan Machacek. This is Matt Squire.
Hello.
You might remember me from such shows as Reactive Summit, and you will certainly remember both of us at the end of this talk, for better or worse. So we'll see how that goes. And we're here to tell you about this thing that we built, a mission-critical reactive system. And hopefully we'll explain why it was mission-critical, what it did, and what does it look like under the hood? And Matt was the man who actually wrote most of the code. So he can give you all the horror stories.
I would say we're equally culpable.
Yes, okay, fine. Right, so what is it? Why? So first of all, you obviously spotted the logo. So Disney streaming services, we're in the business of streaming media. That's all we can tell you. And a lot of the media is live, so live sports events. And I remember back in the days of Cake, when stuff broke, it wasn't it was annoying, but it wasn't a big deal. Try to imagine preventing sports fans from watching their favorite game. It is really mission critical. So what is it?
Right, so as Jan said, we're in the business of broadcasting media. That's live media and on demand. We have these pipelines of processes which do things like transcode video, segment the video, and these live in various locations around the world, and they're responsible for broadcasting sports events. Now, what we wanted was to build a piece of software which can monitor and manage all of these different processes in all these different locations. So we treat these processes like IoT-like devices.
Yeah, historically, they were actually boxes of
Right,
things.
absolutely, yes. So they were physical boxes and, and we want to expose health checks, we want to expose status, and we want to provide a global view of this pipeline to enable the operations teams to be able to make appropriate decisions to anticipate problems before they occur.
Absolutely. And so we built this, and we learned some lessons along the way. So let's just jump straight into it. First thing we thought, well, how about we just do REST, right? That's nice and easy. We're going to do these ephemeral messages to these devices. How hard can that be, right? And then this happens. So imagine that you don't. Imagine, what's wrong? I mean, what's wrong with this?
REST is easy.
What's wrong with this?
I don't think there's anything wrong with this.
There's nothing wrong, right? We send a message to this device, like, say, an HTTP request, or it has some different communication protocol, but it doesn't really matter.
Right, because this shadow is supposed to just be a proxy. All we need to do is forward commands to that device. We only need REST here.
Right, so if we did that, and we did, the first question that happened is something went wrong at the device level. And the first question that the operation team said, what did you send it? And we were like, well, we don't know. We did the right thing. Our code is great. It's this other thing that failed. And so this isn't useful at all. You shouldn't ever lose information. So how about this? We write it to a log file, right?
Oh, that's good, yes. I can open that log in Emacs, and I can now understand everything that's happening.
Right, okay, so that's where the problem is, right? So I don't do Emacs, first of all, so you don't open these log files in VI, but it's usually not structured, right? So if you're writing these HTTP requests to a log file, okay, fine, you can aggregate them, but you want some higher level of integration. You don't want to integrate your services by reading a log file. So we're going to do better, right? So okay, fine. This is a terrible idea. How about DB? We're going to write to a DB. What's wrong with that?
Right. Well, I don't know. Now the operations people can see the data, right? So that's OK.
It is. And remember, we're running in multiple data centers. So there are a couple of data centers in the US, a couple of data centers in Europe. We write to this, where is this database, right? So that would be our first problem. How would this service write to this one global database? And on the architectural level, we would then be suggesting database as a point of integration. And that is a terrible idea, right? You don't want to do that at microservices level. So that goes out, because this service should be able to change its schema. The services that listen, so to speak, on the events on the updates of this database need to know exactly when to run. So we need some sort of queue, right?
OK, yeah, so maybe Kafka?
Maybe Kafka. I mean, OK, come on. It is Kafka. It's durable, right? So all the requests go into Kafka. The queue is durable. So it's sort of like a database, right?
Sure.
we can replay all these events and rehydrate the state. We can say, okay, what happened, what happened, what happened? What's better is this. So I've written this service, and it was terrible. Look, it was basic. And then Matt was in charge of writing some more interesting service that consumes these events, that can do recovery, that can do healing. And he can now do that, right?
Yep.
Because all you do is connect to Kafka and consume these events. And what about the protocol? We had to agree something, right?
I need to know how to understand your messages.
So we ended up internally using protobuf. So there's a published repository of protocol definitions that the device shadow service says, this is what we're going to publish. And these ended up in a GitHub repository. I know. Don't get angry. This is like a shared repository. It isn't. It's just the protocol definitions. What we really wanted to unearth is when Matt submits a pull request to this protocol repository, that prompts all other teams to go, ooh, heads up, right? Someone's changing a protocol. Are they allowed to do it? Is it going to break us? And that turned out to be a really good idea, and we haven't really broken anything at the protocol level.
No, yeah, and in addition, we ended up versioning Kafka topics and doing things like that so that we could deal with breaking protobuf changes.
Okay, so we no longer have ephemeral messages. Everything is recorded. There's a retention policy, right? Of course, you can configure these Kafka topics to keep only so many messages or so many days worth of messages or so many megabytes and gigabytes worth of messages. And you definitely should configure it. Defaults, remember, defaults are your enemy, and we'll get to that in just a moment. Oops, too far.
Okay, cool. So, yeah, okay, so suppose we've got all this durable messaging. We've divided all the responsibilities into lots of microservices. The trouble is that if part of that fails, and then inevitably that failure cascades out into other things, if you don't have some kind of fine-grained supervision hierarchy, all you know is that your thing is just failed.
What's wrong with exceptions?
Well,
why couldn't I just catch an exception?
I think you need a little bit more information. Maybe you need some state somewhere.
Right. And so this is the key of supervision, right? You have this component that supervises other component has its own state. Exceptions might not allow you to do that reliably. So I've written some code on the next slide. So let's have a look at that. Let's have this simple function that makes a device request, right? This is nothing too fancy. And then we run it, right? We make a device request, we send it out, and on complete, we have two options. Like on success, let's not worry about that. That happens all the time, so this is easy. But what about the error? What should we do when the request fails? What do we do in our system? We log it, right?
Makes sense.
And you shouldn't log it this way. Remember, structured logging, this is a terrible idea, but just for illustration. And then maybe we want to retry this. So we could do this. And we shouldn't do this, because this would be like this infinite loop that executes really, really quickly. So we'll schedule a retry for a second later. Let's do that, right? And bear with me, I know, terrible code. And you're looking at this going, all right. So this retries the request a second later. How do we break out of this loop, right? Suppose this connection, this device is always broken. What next? Well, so here's a better diagram. We have, at this level, these device controllers, right? They are the things that make the device requests. Mm-hmm. And what if one of them fails? Let's say 3 times. You have some sort of supervision. This request failed, and failed, and failed. Well, then I can send a message to Matt, who supervises all these 4, let's call them actors for now, and he can make a much more sensible decision.
Right, it's that higher level view of what's going on in the world below me, or whatever this service is, that enables that decision to be made.
Yeah, absolutely. So imagine that the state that you keep in this supervisor is the health of all its children, or maybe every child is now reporting connection error. Okay, maybe it doesn't even make sense to keep retrying. Maybe this node has suffered from some sort of network partition. But in any case, you have this state that lives at this level. You can repeat this hierarchy of state Now, this is a JVM, right? This is easy. Like, if this crashes, if we have to recover, we're still running inside a Docker container, inside a JVM. This is really easy to solve. But of course, these processes, these failures can go up, up, and up, all the way to, say, the JVM level. So what do we, well, okay, well, here's a good question. What do we do when our JVM cannot handle the supervision? What happens then?
I guess it crashes.
Yeah, it system exits with non-zero error code. And then we have Kubernetes, as it happens, that goes, oh, this Docker process that was supposed to be there isn't there. Maybe I should restart it, right? So it's supervision throughout your system, and you want sort of gentle failures, right? The last thing you want is on-error crash, because then that would trigger these cascading failures throughout your system, and they are incredibly difficult to trace, incredibly difficult to fix. So here's another one. And I've heard many, many talks here on back pressure. We'll give you another one.
Sure. So one thing we noticed very quickly was, okay, we built this proxy and it can forward commands onto a device and it can relay the responses back to somebody else. The thing is that two things can happen. Either the device can fail, and that actually causes us to fail because we weren't expecting that, or we can do something stupid and actually break the device downstream. So we need some kind of control over that flow of commands going through, right?
Yeah, absolutely. It's down to memory limits. It's down to what the devices can handle. And suppose our code is the best one in the data center. We could, in effect, DDoS everyone around us. Or if the devices behind us or downstream are too slow, we could crash because we have too many requests queued up and we ran out of memory. So it's a terrible idea. I have code. Look at this. You could do Akka HTTP, right? We've been talking about Kafka. How about this, right? We're going to do Akka HTTP, and this is back pressure baked in. This is fantastic. You have this flow.
Akka HTTP has everything we need.
It actually does. We don't mean it in a sarcastic way. It really does. And you look at this code, you think, this is kind of cool, right? Back pressure baked in, so if there are too many requests, this flow will fail. If there are too many connections open, that pool will start rejecting connections. This is all fantastic, except like we're told that we should be ready for errors, reactive manifesto, right? So let's add that. Let's just add recovery. How about this, right? Let's make a flow that retries. So if the HTTP request that's going out to the device should fail, this is going to come back, try it again, try it again, try it again, within some period of time. And you might be looking at this going, this is fantastic. This is exactly what we're going to do. You could, but here's what we would really encourage you to do. In fact, we have a slide that's somewhat unrelated. You remember this thing? Yes? Okay. Imagine when it was being built. You know, deadlines and features and stuff. And one of the architects was thinking, you know what, I'm just really stuck for time. We're going to go with the defaults. Thermal exhaust vents, never mind those. We'll just accept the default configuration. That turned out to be a really bad idea. And so if I flip back to our code, there is a whole bunch of hidden. It's not hidden. I mean, of course, it's in these config
implied,
files.
but it's not there.
Absolutely. So you have the sizes of the pools. You have TCP Connect timeouts, even on the OS level.
Right, absolutely, because one thing we noticed is that there are certain things that you don't have control over in the JVM. You can control how long you wait for an ask, but TCP timeout or window sizes, these sorts of things, they're all in the kernel, so they're above us.
And you have other settings. I'm not even going to read them out, but what we would really, 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 really recommend is that you pull them all out, type them out explicitly in your config files. And then you can reason a little more about how your flows are going to execute. What is a sensible timeout? You know, what should be the pool size? And we had a somewhat adventurous debugging session when we misconfigured these things. And it was really painful to discover and to reason why this flow is crashing, why our application is rejecting requests, in order to protect the downstream devices. So on the face of it, we were crashing, as in 503s rejecting the incoming request, but we were doing it in order to prevent the downstream devices from crashing, the things that process video. But for our users, it looked like we were broken.
Yep. But the good news is pair programming while one of you is flying across the Atlantic actually works now.
It did work, but let's never do that again. Okay, here's the next one. So we built this, we configured everything, we tried it, and then it's really important to keep an eye on it when it's running. And I know, and we knew, right?
Sure.
But the details of just how much you have to keep an eye on this running application is astounding. And if you don't do it, this happens, right? So Matt did a lot of work on this monitoring. Yeah. I have a diagram, and I'll leave it with you.
It's a very clever diagram. And we've made this distinction between monitoring and observability, which is perhaps a somewhat contentious distinction. I had a look at it this morning, and I found a blog with someone ranting about how observability is this trendy word for monitoring. The distinction we're drawing is that something like monitoring it entails things that your program is constantly telling you. So maybe it's publishing metrics to New Relic, let's say, for example. Maybe something's hitting a health check every so often to see if your application's still there. Observability, on the other hand, has to do with our ability to inspect what's happened. Observability is what we make use of when something goes wrong, and now we want to, say, go to the log aggregator and see what on earth has happened to cause this to crash.
Okay, I think I understand. So what you're saying is that this sort of OS monitoring, if I'm getting it right, and container monitoring is this basic stuff that doesn't need deep knowledge of the application. You can say things like, is the health point returning 200? Okay, without specific knowledge of what this health point is doing. The OS monitoring saying things like, yes, there is enough disk space, and we have enough memory, and containers are still running, right? And so what about these guys?
Right, yes. So
what do we collect, and why do we do it?
Right, well, there's, for example, a really cool library called Cinnamon, which can collect metrics from Akka and push all of that. And then we can go back and look, well, how many actors were there, or how many messages did this actor process during this time window that we're interested in. Similarly, we can instrument the JVM. So we, again, use New Relic, and we instrument the JVM in that way so we can see memory and CPU and so on.
Absolutely. And so when you're debugging, so for me, this observability data is useful when something goes wrong, right? So your monitoring will tell you, I've restarted this Docker process 5 times. It's just not staying up. We get, unfortunately, paged, and we hopefully don't have to get up. It's in the middle of the day, but nevertheless, we have to now look. And what we now want to know is what happened. And we use this data that we collected from our observability layers to say, what on earth might have gone wrong? And the data is obviously stuff that you have from the logs, information about, say, the heap, the thread pool sizes, and what have you. Plus, don't forget your durable messages that you've written to Kafka. And what you really want to know is this one thing that caused the unexpected failure. And then, obviously out it goes into our incident management, which lets us know there is an awful lot of configuration that we found we had to do to tune the right level of notifications that, engineers are dealing with the right stuff and not with noise.
The nice thing is that if your microservices are reasonably uniform in how they're built, then you only need to configure this once, and then you can apply it over and over.
Excellent. Okay. What about this? So I always thought, okay, I'm old school, right? Internet was a beautiful place when I was young. Everything was unencrypted. Everyone trusted each other. That doesn't seem to be the case now. So we have to do this.
Right, yes. I mean, so we've got microservices that are connected together using Kafka topics. What that means is that one service might put a message on a topic which is picked up by another service, and that other service does something. It executes a command. The trouble is that this is a Kafka topic. Anybody can write anything to that. In fact, the protocol, that's in GitHub, so I can get the protocol and produce a message that tells my service to do something that perhaps we don't want it to do.
Absolutely. This sounds a little grandiose, like someone is trying to really get into our infrastructure. You might want to think about this as protection for your own code. Like when you deploy a new version of a service into your pre-production environment, you really want to be absolutely certain that it can never send a message to the production environment. And that if by accident it does, misconfiguration, I made tons of mistakes, that the production environment will reject the message. It will say, look, this is coming from the wrong place. So you want security and you want access control. You want to know that the message came from I have another diagram. So I have a question, obviously, and hopefully you have the same question. These keys, public key infrastructure, we know how that works. So these files, right? Are they written into a Docker container?
No, you don't want to do that. That's actually a pretty bad idea.
Okay.
So the idea we have here is, well, we want to be able to publish a message, maybe that's a command, but we want to be able to authenticate that this message did actually come from a service which is allowed to publish that message. That might be for security, or it might be, as Jan says, simply so that we don't execute commands we didn't mean to execute. Maybe they're part of a test run.
Okay, so public key, private key, I get that.
Yeah.
This token thing we'll get to later. So what you're saying is that if service A wants to publish a payload, just takes the bytes, puts it in the message as it is, doesn't encrypt, doesn't do anything. Service B receives it, but it wants to know, did this payload really come from service A?
Right, and that's where it can use the public key for service A to verify a signature which has been generated by service A.
Oh, I get you, right. So in our envelope of a message that we publish to Kafka, these are the 4 top-level items, really. It's some sort of correlation ID, okay, we can ignore that, token we'll get to, and then we have the signature of the bytes that make up the message that allow us to verify here, right, in service B, that the message really came from service A, and that it was the right service A that produced it, with the right configuration in the right cluster.
Sure, and as for the files themselves, we need to put them in some kind of secrets management system, so thankfully Kubernetes has that already.
Got you, okay, fine. What about this token then?
That's interesting. So suppose we're using JSON Web Tokens, suppose because we are.
We are, but suppose we are.
So JSON Web Token has a section which is the claims that token is making. So service A might make a claim to say, I'm allowed to write to this table, let's say, for example.
Or delete a video stream.
Or delete a video
That's
stream,
a better
right,
one.
yes. That's a very real thing. So that token will contain a set of claims that service is making. And again, the signature includes that claims block.
Got you. And so we can use this as maybe initial trace for the messages. So we can send a message across the entire system, observe it go all the way in, but actually know that it's not going to run, so to speak. It's the service B that receives the message isn't going to act on it. So when we deploy a new version of a system, we can give it a little bit of a dry run, knowing that it's not actually going to do the device requests that we want, but we will observe, observability, remember, durable queues, we will be able to see that everything goes from where it's published all the way to where it should be received without worrying whether it actually works. All the way to service B. Fantastic. Okay, let's get more creative. So we built all this and it worked fantastically well. And then we did this and things got worse.
Yeah, now you don't really know what's going to break until you try it.
That's correct. And you've all heard about doing chaos at infrastructure level. And you've heard about this other streaming company that publishes its tooling that damages infrastructure.
You know, and
whatever, name escapes me.
I've got an idea. What if
yes,
what if we could generate our own envelopes and chaos test at the service level?
So we didn't want to use that. I mean, not just yet. Our hypothesis was that maybe we can break our system assuming the infrastructure is perfect, right? Everything is fine, network connections are fine, everything works. What if we could just send it damaged enough payloads and break it just by being bad users? And we did just that. And I have a couple of examples. So here's one. OK, here's a protobuf message. It has the first line looks like valid protobuf. And then it has these 99 tags, details of protobuf. It's nesting, essentially. Now, that makes this byte array that claims to be message conforming to the protocol X invalid. And so you'd expect this to fail, right?
And that would just the parse exception.
Parse exception, right? That would be reasonable. So we don't want to have these exceptions. So maybe we should first validate if the message is right. So we're going to replace parse from validate. And surely that should return either the instance of decoded message X or some sort of parse error.
Yeah.
Any guesses what this does with sufficient number of 99s? Stack Overflow? Absolutely right. It Stack Overflows. OK, our fault. We shouldn't have been using protobuf. We should be using JSON. How about we try this? What do you think this will do with some JSON parsers? And I'll take the same answer. Stack Overflow. Absolutely right. Boom. Now, we had no idea that this would happen. We just generated these payloads, and we DDoSed ourselves, because it takes a while to compute Stack Overflow, and during that time, your CPU is running. And so if we have 4 cores, all that you have to send me is about 10 kilobytes each.
And just to be clear about that, originally, this Stack Overflow came out by accident from a generated message.
And so we sort of dug into it, and we thought, OK, this is interesting. What else can we do? Well, remember, we have protobuf for the definitions of our protocols. And it's useful, right? It has these types. We know that there's a string. It has only a few types, but useful enough. Yeah. So we know there's, let's say, string, and then there's an array of bytes, and there's some sort of enum. And we have heuristics, right? We know that if a thing is called URI, it's probably a URI. We know that if a thing ends with time, maybe it wants to look like time. So we can generate, right? Scala test, property-based testing style. We can generate this during our testing. This is reasonable, right?
Looks reasonable to me.
This is looking fairly reasonable. Let's now start damaging, given the code below, right? How about this? What do you think will happen now, specifically on this line? Any tips? So we're going way into the past, way, way, way into the past. And we want to schedule a request to happen in negative duration. That's not going to work. Absolutely, right? That's an exception. You can't schedule something for like -4 years. It's ridiculous. How about an easier one? Matt, we figured this out, right? We wrote a unit test that says, oh, OK, how about 2018-13, as in the month? Well, there's an exception here, right? You will have unit tested for us, surely. We have to, believe us. And then you can generate this. I mean, what do you think will happen now? And here's the weird thing. Guess what, Matt? This is going to work. And we look, given the code that we have there, right? It doesn't do any validation. It doesn't do any checks. And so it's going to schedule this request to run so many seconds in the future. Now, that
is the future's problem.
Yes, but it is deeply unpleasant. So imagine you're running your system, your monitoring tells you that it's all fine, and then 5 hours from now, something happens. You have no idea, right? Because you did this work, because there's this scheduled request that's full of complete nonsense. So let's have a look at it again. This you can catch, right? You can unit test for this. This smiley face isn't a good time zone specifier yet. Parse error. All right. Then we saw this. Any tips what's wrong with it? And we thought we were going crazy too, so don't worry. If you're not seeing it, at index 11, if you're not seeing it, you're not the only ones.
There's something not quite right about the T.
So it's a T with a fancy Unicode. This isn't quite T. This is some other character that looks like T, but really isn't. Absolutely hideous, right? You damage your message that comes in, this happens. Terrible. And then, of course, we scheduled one of these damage requests and we got one of those.
Now, hold on a second. This is a JVM bug. This is
Well,
not
clearly.
my problem.
Yes, except durable messages. So when the JVM starts up, it reprocesses all the messages and it crashes again. And again, and again. This was actually pretty terrible. So if you're doing durable messages, if you're doing replays, you need to be prepared for a scenario where you have a durable message and your entire system completely crashes when it reprocesses the message. You need to figure out a way to be able to skip this message, even in situations where the message damages your system like this to the point that it really cannot continue. And we've had those as well.
Oh, yes.
Unfortunately. And of course, there's a final case scenario where you could actually run a request that looks fairly reasonable. It all works. But OK, I'm making fun of Apache struts here. But you could damage the downstream services. So there's a big repository of these naughty strings. If anyone's interested, completely safe for work. But I would really, really encourage you to try every one of them in your unit tests. In fact, write a property-based test that generates as much damaged input, conforming to the protocol, as you can think of. And then, only then, when your system survives this sort of damage, then you can look at damaging your infrastructure. But what you first want to have is a system that survives normal use, right? Including users like us who just send it horrible stuff.
So we've made a lot of claims about what you should do when building a big distributed system. We actually have collected some data to back up some of these arguments. So for the last couple of months, I guess, Jan has been looking across a large number of our projects to try to find some patterns and compare them to issues and that sort of thing.
Yeah, so 2 years ago, I would have had my consultant tie on, and I would have said, Reactive is that's it. Do reactive systems, do Akka, do Kafka, and you'll be totally fine. This will make your systems work wonderfully well. But then I don't have to say that anymore, right? So I thought, is it really true? Does it really make a difference? So what I've done as a bit of a weekend hobby project is I took about 20 of our internal projects that are in production. And I looked at analyzing every file in every commit in every project. And what I wanted to know is what's inside this file? What have we written? I mean, have we written Akka? Have you written thing to talk to Dynamo? Have you written a thing to talk over Akka HTTP, some Spring framework? Who knows what it is? So that was first level. And second thing, so OK, I can show Matt a piece of code, and he'll tell me, this is Akka. But he can tell me one more thing. He can tell me, is this a good idea? Is this
I can tell you for any number of things if it's a good idea or not.
Right, absolutely. So we built a tool that can, given a snippet of code, it can tell me what is it, and based on Stack Overflow, I know, we copy and paste, I'm sure you don't, but based on Stack Overflow sentiment around the code, it can indicate whether this piece of code is a really good way of achieving whatever this code presents to be. So that was interesting, and then I combined it with matching production data from PagerDuty. And so the question was, what makes a difference? What's the kind of code that we should write? Now, we collected a lot of stuff. Sadly, this is our studio. Well, you know, it's better than Eclipse. Ooh, maybe I shouldn't have said that. Anyway, we collected 750,000 of observations. So this is 24 variables. So this is things like, what's Akka? Does this file contain Akka? Is it a good idea? Does this file contain Spring? Is it a good idea? Does this file contain structured logging? And is it a good idea? And we have many files, obviously, in our projects, because this goes over every commit. We have some incidents. The numbers aren't real, so don't try to deduce how many incidents we have. I had to fake the numbers somewhat. But this I didn't fake. Your question would be, what's a really good example of doing that? I have to step in closer. what's a really good way of doing performance testing in an actor? And we have a tool that can point you to these 3 files. In all of our code base, these are the 3 best examples of doing performance testing with actors. This is really neat.
Well, we pretty much automated software architecture then.
We've automated my job. I like that. I don't have to work at all. I have a computer that does my job for me. When someone comes in and says, what's a really good way of doing, what about this bottom one, right? What's a really good way of doing logging, structured logging that is, with Kafka? And it points us to these 2 files in our internal GitHub, which is pretty neat. And we have other variations, right? We have what's the worst idea of doing, what's this? DynamoDB. I could have ended there, but really bad idea of doing performance testing with DynamoDB. So like, don't do this. If you look at these 2 files, whatever's inside, don't do that. And of course, you can compare multiple projects together and yada-da-da-da to like paint this entire technological landscape of what we have. So this is the thing you've been waiting for. What matters? What should we do? Where does it come from?
Suspense.
Ready? Suspense? Well, so we measured this. I have more graphs, but I'll give you commentary around it. It's these red, orange dots, they're sort of weighted measurement of production performance. By that, we mean fewest number of incidents, quick time to recovery, fewest number of escalations. And the histogram of what's a distribution of files that contain code that do performance testing. Are they a good idea? Are they a bad idea? Are they good idea? Are they the code inside? Is it a good idea? Is it a bad idea? And we have the same thing for reactive and every single one of these 24 variables. And after careful analysis and my horrible R, the results are in. So 4 things, clickbait, right?
Sounds like
but
a
we're
LinkedIn
not,
article.
Yeah, no, we're not on LinkedIn. Let's do something better. Throughout, this is the kicker. Throughout commit history. Not at the end. Right from one of the first commits. These 4 things. Matt, any commentary on that?
Yes, I mean, structured performance tested logging. We've already talked about, the need for proper logging, structured logging, and that includes, of course, journaling too, which we mentioned. Monitoring, distributed tracing speaks to, again, monitoring and observability. Performance testing, so we haven't spoken so much about that, but it's something that we've got into the habit of doing right at the beginning of a project. Now, you might think, well, how do I test my API before I've written my API? I don't know. You test the health check endpoint, because if your health check endpoint can't handle 1 request a second, then you're off to a pretty bad start.
That's for sure.
And yeah, a reactive architecture code, which is durable messaging, supervision hierarchy,
Absolutely.
observability, so forth.
So back pressure, event-driven systems, supervision. That's the kicker. Performance testing, again, we can't stress it. There were a couple of talks at this conference about this topic. You have to start right from your second commit. Have a performance test and run it continuously. Monitoring and distributed tracing. Distributed is the keyword. I put it in brackets, but that really, you have to have it. The last thing you want is, this microservice failed because it received a message. But where did that come from? Right? You'd be looking at this message in your logs from your observability layer, thinking, no one sent this message. Maybe the bug is actually in the service that's upstream that produces damaged message. You need to be able to see it go all the way throughout. And if you're going to do logging, do structured logging, that's for sure, but performance test it. We had problems when our logging was the thing that was bringing our application down because it wasn't keeping up with the performance of the application. So I don't know how much more to stress about this, but these are the 4 things.
A similar anecdote for the logging one, not only have we had situations where things have failed because of logging too much, but also if one thing is broken and it's constantly logging I can't reach this other thing, what do I do? And suddenly it fills up the disk on the container and everything falls down.
Absolutely. So we're right early. This is fantastic. You're going to have earlier lunch. We have actually summarized this in 2 papers that they're being reviewed internally, but hopefully we'll be able to publish them out pretty soon. One on the protocol chaos testing. So this is all the property-based testing that you should do and how you can damage your applications. Think Stack Overflows. What should you do? Should you sign your messages? Should you just checksum them? And what are the implications of that? And a second paper that deals with this sort of large-scale knowledge sharing and discovery and answers the question, what really is the important code? Now, we won't quite be able to take your questions because it's a big company and we might not be able to give you the answer that you want to hear in full, but come and talk to us individually and we will definitely be able to give you the context between the lines. But one more thing I'll say before we release you for lunch is we're here and we hear a lot about Scala and Akka, and a lot of you might be sort of thinking about the question, does the language that we use to implement these services really matter? Should I jump onto the Scala bandwagon? Should I stick with Node.js?
No, I think Rust.
Rust.
Rust is cool.
Well, so given our project and this analysis, turns out that language makes no difference. None. Frameworks do. So Akka made a huge difference as good implementation of reactive patterns. Latest Spring framework made a huge difference. Those were successful applications. Interestingly for you strongly typed people, Scala Z made a big difference. So Scala Z showed this high correlation with good production performance. We don't think it has anything to do with Scala Z. We think it has to do with people were forced to think about their code a little more. So don't worry about Scala Z as such. But the good news is you don't have to rewrite your services in the latest flavor of anything as long as you follow the 4 rules that we showed you earlier. And well, that's it. That's all I have.